All right, welcome back. I have two more lectures that I'm going to do. This one is to let y'all know how to prepare a buffer. I figured that this would be helpful for you because you'd cover this in lab. And then we'll talk about equivalence points. So those are the two more video lectures that are going to be available. So the first one is how to prepare a buffer. For example, sodium phosphate buffer, which is an example in your book, example 17.5 that I'm going through. Now, this is useful because a lot of times, especially as biologists, you're going to need to make a buffer. You're going to need to make sodium phosphate buffer, for example, which is a version of PBS. And I say a version because there's some other stuff that's involved in there. But so since you've always wanted to know that, we're going to go ahead and talk about that. All right, so the first thing that we're going to do is remind ourselves that in order to make a buffer, so we want to make a buffer at a certain pH. We want it to be a pH of 7.45. And this is useful because we know that this is the pH that's usually of your blood, right? And so a lot of times we as biologists and chemists will make this so that we can simulate the conditions of the human body, right? Okay, great. So we want to make a buffer at a particular pH, and we need to know what ingredients to put in so that we can achieve that particular pH. So the first thing to start with is the Henderson-Hasselbalch equation, which is pH is equal to the pKa plus the log of, I'm just going to say conjugate base right now, over acid. Okay, so we are going to make sodium phosphate buffer, but what's important about it is that when we're talking about phosphate, we are considering phosphoric acid. Phosphoric acid looks like this. It's what's called a triprotic acid. Why? Because there are 3 protons that are in it. It is a weak acid. Yes, it is entirely a weak acid. Okay. So, in order to figure out how much phosphate we need, how much phosphoric acid we need to apply it to this Henderson-Hasselbalch equation. So we need to know the pKa, we need to know the concentration of conjugate base, and at least the ratio of conjugate base to acid. So, and we want our pH to be equal to 7.45. So this equation is going to be equal to 7.45 pKa plus log of, and I'm going to leave this blank for right now, this conjugate base over the acid, because we need to figure out what exactly we're going to use for that. So, all right, so I got to go to the other side of the board. It's a little tighter at my house doing this, but it's working. All right, so like I said, phosphoric acid is a triprotic acid, and so it undergoes 3 reactions. What do I mean by that? We didn't talk about this in chapter 3 because, not 3, we didn't talk about this in chapter 16, but in chapter 16 for triprotic acids, and I'm seeing that this is kind of hard to see. Let's use black. There's a dissociation reaction that happens for each one of the protons that come off. So here's the first one. And I'm going to move this over already. Let's try this again. Where's my eraser? Far. Not here. Okay, great. First we start with triprotic acid. The first dissociation, one proton comes off and we end up with H2PO4 minus. Okay, hold on. This lighting isn't that great, is it? It's worse. All right, we'll have to work with that. Okay, hopefully my shadow will mask it. Okay, one proton comes off and we have, and it's hard to see, so let me try this again. H2PO4 minus, right? Okay, so this is our first reaction. This has a Ka, and we're just going to say 1 because this is our first reaction, dissociation reaction. Second dissociation reaction takes the anion, H2PO4 minus, and it pulls off another proton. If we pull off another proton, okay, so you notice the first proton that we pulled off, the anion has a -1 charge. The second one that we pull off now is going to have a -2 charge, and it has a pKa. Not a pKa, a pKa for the second reaction. And then third, we take this anion once again, and we pull off the last proton. And after we pull this last proton off, that means that we're left with just a phosphate anion. That is a -3 charge. So the minus reflects the proton that's gone, right? So we can have a balanced charge here. So the first one pulls off one proton. We end up with H2PO4 minus. Then we pull off another proton. We end up with HPO4 -2. And then we have our -2. We take off our last proton, and we end up with phosphate ion. And this also has a pKa value of 3. So these pKa values, we can look these up. And why are we going to want to look them up? Because we're going to want to figure out what those are, and then we want to figure out the pKa value. Now what we're looking for, maybe I should still just put it in as a placeholder. This is conjugate base. Over acid. Now we remember that when we are, one thing that we remember from what I lectured on yesterday, or at least in the videos, is that pH is very close to pKa. So this value here, this log conjugate base over acid, is it's usually pretty small. And sometimes we can assume it to be almost 0, right? We talked about that. So we could say our pH is about similar to pKa. So if we are building or design, if we're mixing a buffer or making a buffer and we want it to be a certain pH, the idea is that we need to start with using a pKa value that's very close to the pH that we want to use. So that's why we need to look up these values to figure out which one is the best. So I'm going to write those down over here. So for Ka1, The Ka1 value is 7.5 times 10 to the minus 3. The Ka2 value is 6.2 times 10 to the minus 8. And the Ka3 value is 4.8 times 10 to the minus 13. Okay? So those are our values. Okay, so now what we need to figure out is pKa. And how do we figure out pKa? We take the minus log. So we already know, we're looking these up. And those are here. We figure out the minus log, because that's what pKa means. Let's do this. pKa is equal to the minus log of 7.5 times 10 to the minus 3. That's pKa1. pKa2 is minus log of 6.2 times 10 to the minus 8. I'll show you in a second. I know I'm covering it. Ka3 is minus log of 4.8 times 10 to the minus 13. Okay? So that's all we did, is we did our P operator, right? Okay, what are our values? Well, after we calculate this, we find that we have, for the first reaction, the pKa value is 2.12. So pretty acidic, right? The next one is 7.21, and the last one is 12.32. Now, remembering that pH is close to pKa, we want to pick a reaction that will give us a very close pKa to 7.45, and that is going to be this value, 7.21. And 7.21 relates to pKa2, which came from this pKa, and this pKa came from reaction 2. So reaction 2 gives us a pKa value that's very close to 7.45. So we're going to use the second reaction to calculate how the conjugate base and the acid, the ratio that we need so we can make our buffer. Now, for example, if we wanted to make a buffer that was very acidic, that had a much lower pH, then we would use pKa1. If we wanted to make a buffer that was extremely basic, then we would use pKa3. But we know we want it to be close to 7.45, so we're going to use the second equation to plug into our Henderson-Hasselhoff equation. All right, so let's do that. So since we are using equation 2, let me try to scoot on by. This is crazy. It's working now, sort of. All right. We rewrite 7.45 is equal to 7.21. Yeah, that's what plus the log of conjugate base. Okay, so now we can identify what our conjugate base is and what our acid is. In equation 2, we start with this H2PO4 minus. That is our acid that dissociates, pulls off a proton, and then we have a conjugate base of HPO4 2 minus. So let's put that information in. So on top, our conjugate base is HPO4 minus 2, And on the bottom is our acid, which is H2PO4 minus 1. Okay, so now what we can do is we can solve for this. So if we subtract on either side 7.21, we end up with 7.45 minus 7.21 equals 0.24 is equal to the log of HPO4 minus 2 over H2PO4. Okay, we can get this. We want to know what the ratio of conjugate base to acid is. So HPO4 minus 2 over H2PO4 minus is equal to, so this is equal to, in order to get this quantity, we have to take 10 to the 0.24. Okay? This is the analog of this. Kind of like when we did the analog with, we had for pH, the log, the negative log, and then we did 10 to the negative pH. It's the same thing. I moved this to the other side just so that we could show that we were taking, because this is log base 10, it would be 10 to this quantity and 10 to this quantity to then get just this. Yeah, that's what it is. 10 to this gives us just this quantity, and we have 10 to the 0.24, okay? So when we calculate 10 to the 0.24, we get a value of 1.7, okay? So the ratio of HPO4 2 minus to H2PO4 minus is equal to 1.7. Okay, so I need to do some erasing. So we are clear here. We understand how we got and why we're using this equation, because when we took phosphoric acid, which is what we need to use to make sodium phosphate buffer, we need to have some phosphate ions. We take phosphoric acid, we break it down. Phosphoric acid first takes off the first proton to give a pKa for that first reaction. Then it takes off another proton for the second dissociation reaction to get a pKa of 2, and then we take off the third one to get just phosphate ion. We looked up the pKa values in your book. I think it's table 16.5 or something like that, to find out the pKa values for each of these right here. And once we knew those, we were able to, and you see it as either the acid or conjugate base. They provide both of those. Ka values. Then we took the P operator, which was the negative log of this value, to give a pKa of, for equation 1, 2.12, for equation 2, 7.21, and equation 3, 12.32. We chose the pKa value 2 to represent the conjugate base and the conjugate acid, or the conjugate base and the acid that we're going to use to make our buffer. And we start with this 7.21 because it's very close to the value that we want to use. So we put it into this equation. We know that our conjugate base is HPO4 as shown here. We know that our acid is H2PO4 minus, and then we solve. And we solve for this ratio, which is HPO4 minus over H2PO4 minus. We do that by subtracting 7.21 on both sides to get 0.42. Then we take 10 to the power 0.24 to get just this quantity here, which is then shown down here. So I show 10 to the 0.24 power that you can put in your calculator. You put it in and you get 1.7. All right, so I'm going to do some erasing. Hopefully I'll find my eraser. Oh, there it is. Okay, great. All right. So now what does this mean? What does this 1.7 do for us exactly? Because we still need to know what we need to put in our flask, basically, so that we can make our buffer. What this means is that we have that the ratio is 1.7 to H, concentration of HPO4 minus 2 to H2PO4 minus. So what that means good. So what that means is that we have to have 1.7 moles of HPO4 minus 2 to a ratio of 1 mole of H2PO4 minus. Okay? I know what you're thinking, because this is what I thought. Oh, I just multiply by this, and then I can... Don't do that. Just assume it as it's 1.17 moles to 1 mole, 1.7 moles of HPO42 minus to 1 mole of H2PO4 minus. Okay? So that means that you need to, in order to make a 1 molar solution of sodium phosphate buffer solution. We know that's normally not 1 molar, but I'm just saying, if we make 1 molar of that, then that means that we need 1 mole of HPO4 minus and 1.7 moles of HPO4 minus, and we need 1 mole of H2PO4 minus, okay, to make 1 molar solution. We know that 1 molar is 1 mole of solution per 1 liter, right? So the liter is, we have 1 liter volume. So what ends up happening is we end up using 2 forms of sodium phosphate. We use NaHPO4. This is Na2 HPO4 minus 2. We want 1.7 moles of this, and we use Na. This is where the sodium part comes in. H2PO4. I have a minus 2 only so that we can just remember that this is minus 2 and that this is minus 1 here, okay? Because that becomes sort of important. So that we want 1 mole of this, right? Okay, great. So I know this is getting long, but we're going to get there. Okay, so we need 1 mole of, or 1.7 moles of sodium. This is what's called dibasic because it has a minus 2. And then this is monobasic, which is minus 1. So if you ever wondered why you had to use dibasic and monobasic, this is the reason. Now remember, these are salts. So they are strong electrolytes. So when they dissociate, we end up with just the conjugate bases that show up, which are then used for this ratio so that we can make our 1 molar solution at a pH of 7.45. So all you would need to do is use the molecular weight to get to the number of grams of, this is dibasic, and the number of grams of monobasic. So the molecular weight of dibasic is, I don't want to show that because I don't want to get too deep in that. But you would take the molecular weight in grams of the dibasic, which you could look up. Maybe I should put it. Yeah. Molecular weight of dibasic, which is this, HPO4 minus 2, is 141.96 grams, and the molecular weight of mono basic, which is this, is 119.98 grams. This is per mole. So you have moles that you want to use molecular weight to get to grams. Once you have grams, you're going to take those grams of the dibasic salt and mix it with the number of grams needed for the monobasic salt by multiplying molecular weight. You mix that in with 1 liter of water, and then you end up with 1 molar solution of buffer. If you wanted to have a 0.1 molar solution, for example, then you would multiply 1.7 times 0.1 to then alter these numbers to then put into your flask, and you would still have use 1 liter of water. So instead, if you wanted a 0.1 molar solution, which is what we make in the lab usually, it would be 0.17 moles and 0.1 moles. Now PBS, which is also a version of sodium phosphate buffer, is 0.1 molar, 0.001 molar is PBS, the concentration of PBS, but there is also some sodium chloride in there. This is extra, but I'm just saying. If you wanted to make a 0.001 molar solution, then this would be 0.017 moles, and this would be 0.001. You would use the same formulas to then figure out the grams. You'd mix that in with 1 liter of water, and then you would be able to make a different concentration of buffer. So that's how we make buffer.